we are about to tackle a really fundamental shift in how we think about writing software.
It's a huge shift.
Yeah, because if you, the learner, have mostly been in that world of procedural programming.
Right, where it's just a sequence of functions one after another.
Exactly, step-by-step procedures. You already know the pain point that's coming as your project gets bigger.
Oh, absolutely. That model feels fine at first, but you eventually hit a wall of complexity.
And that's when functions start needing access to, globally shared data. And all of a sudden, debugging is just a nightmare.
It's spaghetti code. And that's precisely why object-oriented programming, or OOP, is really the paradigm of choice for almost all large, complex, modern systems.
Okay, so what's the architectural why behind that?
Well, the core idea is that object-oriented design, or O, just makes software vastly easier to maintain and improve over time.
So our mission for this deep dive is to really break down the concepts that make OOP so powerful, especially in Python.
And the whole focus shifts. You stop thinking about procedures and start thinking about creating objects.
Right. And these objects aren't just like bags of data. They're these self-contained units that bundle two things together.
The data, which we call attributes or properties.
The things that maintain the object's state.
And the functionality, the methods or functions that actually operate on that data.
And feels more intuitive somehow.
It is, because it maps directly to concepts in the real world. A class definition is basically a blueprint for a real-world thing, and the methods are how that thing interacts with the world.
It's funny. You've probably been using OOP all along without even realizing it.
That's a great point. Every time you use a fundamental data type in Python, a string, an integer, a dictionary, those are all actually built-in classes.
So when I call .append on a list, I'm actually calling a method that belongs to the list object.
Precisely. And the class keyword is what gives you, the programmer, the power to define your own custom data types. A class is that blueprint.
Okay, let's make this concrete. The source material uses a great, simple example, a point class.
Perfect. To represent a point in 2D space.
So the class needs to define its attributes, which would be X and Y.
And its methods, which are the actions it can perform.
And when I actually create a specific point, say P1 equals 0.10, 20, that's called an instance of the class.
Right. The object instance, P1, is what holds the actual state, the data. So X is 10, Y is 20.
And to get to that data, we just use dot notation. P1.x gives me the value.
And if you had a method, P1.getDistance would run that function. It's that simple.
Okay, as soon as you talk about creating an instance, we have to talk about special methods. You can't really build an object without a constructor.
Exactly. The most important one is init. That's the constructor. When you call 0.1020, Python is secretly calling that init method for you to set up the object's initial state.
I know the source mentioned the del destructor, but is that really something we should be focusing on in modern Python?
That's a really sharp question. And no, not really. While del exists, Python's automatic memory management makes it kind of unnecessary most of the time.
So what's a more practical special method?
Oh, a streamery. Definitely stream.
For debugging. Because if you just try to print an object, you get that ugly memory address.
Right. But if you define a str method, you can tell Python how to represent your object as a human-readable string.
So instead of that memory location, it could print point at 1020.
Exactly. The object can report its own internal state. It's a core part of encapsulation.
Okay, so that brings us to the core of why encapsulation is so important. My P1 object is mutable. I can just write P1.x equals 50.
You can, but you shouldn't.
Why not?
Because that's how you create bugs. Unintended side effects. If any random part of your program can just reach in and mess with the internal data of an object, you lose all control and predictability.
So the better approach is all about control. The class itself should manage its own state.
Absolutely. So instead of just changing the coordinate, the source suggests you add a designated method like move newx newy. That method is the only clean, controlled way to modify the points data.
Which immediately brings up access control. In Java or C++ add, you have keywords like private. Python doesn't have that.
And this is a huge Python nuance. It relies on convention, not enforcement. By default, every member is public.
It's a handshake agreement between programmers, then.
That's a perfect way to put it. The community agreed on the underscore convention. A single leading underscore, like internal data, is a signal. It's a polite request saying, hey, treat this as private, don't touch it from the outside.
But the interpreter won't stop you.
Nope. It's just a convention. Now, the double underscore is different.
Right, like secret data. That's more than just a suggestion, isn't it?
Much more. A double leading underscore triggers something called name mangling.
Name mangling.
Yeah, when Python compiles the class, it secretly renames that attribute. It adds the class name to the front, so it becomes something like class name secret data.
Ah, so if I try to access my object.secretData from the outside, it just fails because
Yeah.
that's not its real name anymore.
Correct. It's not true privacy, because a determined programmer can figure out the mangled name, but it's a very strong barrier against accidents.
That clears up a lot. Okay, so once we're managing state with methods, we want to make using the object feel natural. That's where operator overloading comes in.
It's a cool feature. It lets you redefine what standard operators, like the plus sign, do for your custom class.
So for our point class, instead of writing some clunky method call like p3 equals p1.addPointP2,
Yeah, you can overload the add special method, and then you can just write p3 equals p1 plus p2.
it just feels more intuitive. The goal is always to make your custom class as easy to use as possible.
Always. And as your models get more complex, you find that objects are often made up of other objects.
Which brings us to composition.
That has a relationship.
Okay, let's unpack that.
Mm.
I see a lot of people reach for inheritance when they should be using composition.
It's a common mistake. Composition is when a class includes another class as one of its members. The source example of a rectangle class is perfect for this. A rectangle has a top left corner.
And it has a bottom right corner.
Yeah.
And those corners are points.
Exactly. So instead of storing 4 numbers in your rectangle class, you just store 2 instances of your point class.
And you're building a complex object out of simpler tested ones.
It's a huge win for code reuse and clarity.
All right, this next part is, I think, where things can really make or break good OOP design in Python.
The method types.
Yes, the 3 distinct types of methods: instance, class, and static methods.
And understanding which one to use is critical. It's the difference between really using OOP and just, writing procedural code inside a class.
So let's start with the one we already know, instance methods.
These are the workhorses. They're the normal methods. They always take self as the first argument, which points to the specific object instance.
And their job is to act on that instance's unique data.
Correct. They can freely access attributes and call other methods on that same object. They need an object to exist.
Straightforward enough. What's next?
Next up are class methods, which you mark with the @classMethod decorator.
And these take sleals as their first argument, not self.
Right. Creasels points to the class itself, not an instance. And crucially, you don't need an instance to call them. You can just call it directly on the class, like point.someClass method.
Okay, but if they don't have an instance, what data can they actually work with?
They can only access and modify class attributes, so variables that are shared across all instances of that class.
And what's a common use for them?
Factory methods. They're often used as alternative ways to construct an object, like creating a point object from polar coordinates instead of Cartesian.
I see. So they manage the class, not the instance. That leaves the last one, static methods.
Marked with @static method. These are the most isolated. They take neither self nor clails.
They're just functions that happen to live inside the class's namespace.
Basically, yeah. They're utility functions that are logically related to the class but don't depend on any state.
I've seen these misused a lot. What's the key rule to know when not to use a static method?
If the logic inside your method needs to know anything about a specific instance's state or anything about the class's shared state, it should not be a static method.
So for our point class, a function to convert radians to degrees, that would be a perfect static method.
A perfect example. It's related to coordinates, but it doesn't need to know the x or y of any specific point.
If you get the difference between instance data, class data, and no data, you've pretty much mastered method types.
You really have.
Okay, let's shift to a very practical problem. Object identity and copying. This trips up so many people.
It really does. With a simple integer, it's easy. But if I have object B,
Object A.
you haven't made a new object. You've just created an alias, a second name tag for the exact same object in memory.
It's like putting a second label on the same jar of cookies. You use one label to take a cookie, and the change is reflected no matter which label you look at, because there's only one jar.
And this gets really tricky when you have nested objects, like our rectangle that contains point objects. That's a shallow copy. That's where the real trouble starts. With a shallow copy, the rectangle itself might be a new object, but the point objects inside it are still shared.
So changing the corner of the copied rectangle would also change the corner of the original one.
Potentially, yes. Which is a bug waiting to happen. So for a truly independent copy,
You need a power tool. You need deep copy.
you need deep copy. It recursively copies everything, the container and everything nested inside, guaranteeing the new object is completely independent. It all comes down to that concept of sameness.
And of course, objects can be passed to functions as arguments.
Yep, and they can be returned from functions too. It's how we build dynamic systems.
So let's try to bring this all together.
Well, the real value of OOP is organization. It's about bundling data and the functions that work on that data into these neat logical units. You stop telling the computer how to do every little step, and you start modeling the things in your problem.
Whether that's a team class for a sports league table or a triangle class to calculate an area.
Exactly. OOP provides the structure to manage that complexity.
This has all been about identity, really. The identity of a class, of an instance, and even the methods.
That's a great way to summarize it.
And that leads to a final, maybe slightly provocative thought for you to go and explore. We've talked about how passing an object to a function lets that function operate on its state. So here's the question. When you pass an object as an argument to a function in Python, how can you write a test to prove definitively whether that object is being passed by value or by reference?
That is the ultimate test of identity and mutability. We really encourage you to write a little script and find out for yourself.
Thank you for joining us for this deep dive into object-oriented thinking. We'll see you next time.